Welcome to AP Unit 1.5, video number 1. Our topic is atomic structure and electron configuration. And in this video, we're going to answer the essential question: what is the difference between the electron configuration for an atom in the ground state versus an electron in an excited state? And as always, we're going to use our main ideas, questions, and prompts to help answer the essential question in the summary. So let's go ahead and get started. So I have here a definition, or I've defined the ground state electron, and it's referring to an electron in its lowest possible energy level, and then it is also going to be the most stable form or stable state the electron could be in. And it also has the least amount potential energy. And I think that's all I really want to go over there, highlight out of that paragraph there. I'm not going to read that to you. So what we're going to do is we're going to also write an annotated example for how to write the electron configuration for an atom. And I'm going to do this a couple ways. I want to use an abbreviated electron configuration, the full electron configuration, and then you may be asked to write the electron configuration just for valence electrons, and I just want to make sure you understand the difference between writing the full electron configuration and those of just the valence electrons. So let's go ahead and get started. Let's say that we have an element we want to write the electron configuration for. Well, let's go with magnesium as our example. So let's use magnesium. And in magnesium, we have to recognize, and you should know this from your previous chemistry course, that when we write electron configuration, we're showing where the electrons are by energy level, and then also by their orbital. So we have 4 of these orbitals: the s, the p, the d, and the f. And we should recognize that the s block or the s orbitals can hold 2 electrons. So they can hold 2 electrons. The p can hold 6. The d can hold 10, and the F can hold 14. We can even see that on our periodic table. So in energy level 1, and this is when we say 1s, just to make sure we're all on the same page, when we say 1s, for instance, this number here is referring to the energy level. We should know that. And then this is the orbital. And then if we place a superscripted numerical value over the S, P, D, or F, or the orbital, then that's telling us the number of electrons. And I didn't get myself enough room to write here. Number of electrons, let's say that. All right, so we understand where that is coming from. So things that you should know is in energy level 1, here's energy level 1, as indicated by saying 1s. It only has the s orbital, and the s orbital can only hold how many electrons? 2. That's going to be a major concept that we bring up later on. So understand that now, that energy level 1 only has the s orbital, and therefore it can only hold 2 electrons. Whereas all of the other energy levels, notice, have at least s and p. So energy level 2 has S and P, energy level 3 has S, P, and then also D. But we notice as we read through the periodic table to get our configuration, we read it 1s1, 1s2, 2s1, 2s2, 2p1 through 2p6, 3s2, 3p1 through 3p6, 4s1 and 4s2, and then after 4s, we backfill this d orbital in the 3rd energy level, and there's 10 electrons there. So it'd be 3d1 through 3d10, and then 4p6, 5s2, 4d10, 5p6, and so on and so forth. And in your previous course, we used what we called the yellow brick road, which follows this, and this is mirroring what we see with the periodic table. So it goes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. Notice that still follows it. 4p, 6, 5s2, 4d10, 5p6, 6s2, and then it's going to go into the F block. All right. So after we get to I'm sorry, I may have went 5s2, 4d10, 5p, 5p6, 6s2 after the sixth. It goes to the F block. And so the F block, which is 2 behind, so here's energy level 6. D block is 1 energy level behind. The F block is 2 energy levels behind. So it's 6s2. Notice this, and then it goes to 4f. So then it would be there's 14 electrons there. So 4f14, and then 5d 10, 6p6, 7s2, and so on and so forth. So you will not receive this chart. You will not receive this yellow brick road chart on your AP exam. You can draw that for yourself, or you can just make sense of the periodic table, which I think is easy enough to do. So let's write this for magnesium. We know magnesium is right here, and it's an energy level 3. We can think of these period numbers as being the energy levels, but we just have to recognize that when you get to energy level 3D, that is behind that by 1. So we have magnesium, and we notice that it is in 3s, and that in particular it is 3s2. So it's right here, 3s2. So we can end our configuration with 3s2, and then just simply write our configuration up to 3s2. So we have 1s1, 1s2, so we'll write that down, and then 2s1 and 2, so 2s2, and then 2p6, and then 3s2. So we're done. So how do we know whether we have the right configuration? Well, we know we have energy level is represented by the larger numbers here, and then we know the suborbitals, and then we also know that these numbers superscripted represent the number of electrons. And so if we have the same number of electrons as we do protons, if we're a neutral atom, then we know we have the right configuration. So magnesium has an atomic number of 12, so it has 12 protons. Well, if this is magnesium and it does not have a charge, then it's an atom of magnesium and it has a neutral charge, so it should have 12 electrons in its configuration. So we count 2, 4, 10, 12, and we see that there's 12 electrons there. Now, there's another way of writing this. So this is the full electron configuration. There's another way of writing that. Another way that we could express that is using an abbreviated. When we use the abbreviated, we take everything up through the noble gas prior to the atom that we're writing the configuration for. So if we notice for magnesium, the noble gas previous to magnesium is neon. And so what we would write, and this would still be a valid configuration for magnesium, we would write, whoop, something happened there. We would write neon in a bracket and then 3s2. And so this is accounting for all the electrons up through neon and then 3s2. So that's how we express the full configuration and then also the abbreviated configuration. Now, if I were to ask you to write the electron configuration just for the valence electrons, well, what are valence electrons? We should know that valence electrons are only the electrons in the highest energy level. So we know out of energy level 1, energy level 2, and energy level 3, energy level 3 is the highest. So we're going to only express those electrons in the highest energy level. So if I'm writing this just for valence electrons, I don't know what I just did there, but valence electrons, configuration for magnesium, we're going to just write 3s2. And so that's the difference between your full configuration, an abbreviated configuration, which accounts for all the electrons in that atom, and the valence electrons, just the valence electron configuration, meaning you're only discussing those in the highest energy level, all right? Not all the electrons in the atom itself. Okay, so make sure you are able to do that. And then just to do one more, let's knock that out real quick. Let's do one for bromine. Let's do one for bromine. So here's bromine. And if we wrote the full electron configuration for bromine, here it is right here. We notice that it is in energy level 4, and it is 4p1, 2, 3, 4, 5. So we're going to stop at 4p5, and we can start always at our first energy level. So it's 1s2, then we got 2s2, 2p6, 3s2, 3p6, 4s2. I didn't give myself enough room. Move this over. 4p5. All right, and then lastly, 3d10. So we went 4s2, 3d10, and then 4p5. So this is our full valence electron configuration. Now, if we wanted to use the abbreviated electron configuration, we're going to write the configuration for all the electrons represented up to the noble gas prior to bromine. And so we can see very easily that argon is the noble gas prior to bromine. So what we in the noble gas configuration for argon is 3s2, 3p6. So everything through here is argon. So when we write our expression, bromine would be bracket argon. But what comes after that? Well, we know 4s2, 3d10, and then 4p5. All right. So we have to count those 3d10 electrons after the noble gas configuration because they come after argon on the periodic table. And then if I asked you to write just the valence electron configuration for bromine, then you would look at just the highest energy level. The highest energy level is 4. So we would say 4s2, 4p5. And that's all there is to that. All right, so hopefully you'll be good to go on writing the electron configuration, and you can interpret an abbreviated electron configuration. You can write an abbreviated electron configuration. You can write the full electron configuration. You can write the electron configuration just for valence electrons. And quite frankly, you should be able to identify an atom by its electron configuration. So if you were just given either one of these expressions without that same bromine, and you said it was a neutral atom, you should be able to identify bromine from those. So just be aware of that as well. And I think that's a pretty easy task. All right. And then let's go to another example, and the annotated example. Got annotated spelled incorrectly, but that's okay. We'll live. So there we go. Yeah. So it says write the ground state electron configuration for an ion. Okay. So ions, as we know, are atoms with a charge. And how do atoms get a charge? They get a charge by gaining or losing electrons, all right? So if it forms a cation, then it's going to gain an electron. If it forms an anion, it's going to, if it forms a cation, it's going to lose an electron. And if it forms an anion, it's going to gain an electron. So, yes. So let's look at an example of magnesium again. And so for magnesium, let's show the ground state electron configuration for magnesium 2+. So we know how to write the electron configuration for magnesium. We know that it was 1s2, 2s2, 2p6, 3s2. And so this would be for a neutral atom. But how did magnesium become magnesium 2+? Well, it formed a cation, and cations lose electrons to form the positive charge, right? So it has to lose the electrons. So it lost its electrons in its valence shell, and so there's its electron configuration. All right, and it has the noble gas configuration when it forms that ion. What's the noble gas configuration? So we see that it is magnesium, it lost magnesium and sodium electrons, so it has the same electron configuration as neon. All right, it has the same electron configuration as neon. So it has a noble gas configuration after it forms an ion. All right, let's look also at bromine. All right, we're going to look at it because it forms an anion. So we have bromide. We're going to show it as, now notice that in both of these examples, I'm showing these with a charge. All right, showing these with a charge. So we know the electron configuration of bromine, we can even see it above, is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then 4p5. So this would be for a neutrally charged bromine atom. But we are trying to write the electron configuration for bromide, which has an electron, which has a negative charge, and it's an anion. So how does it become an anion? Anions, they do what? Gain electrons to form a negative charge. All right. And so we have to show that extra electron, and it's going to be shown right here on its highest energy level in orbital. So this is going to be 4p6. Now, it also has a noble gas configuration. So anytime we're forming these ions, we should see a noble gas configuration. If you're forming a cation, you get the noble gas configuration before. So here's magnesium. What's its configuration as an ion? Neon. Neon comes before magnesium. If you look at bromide, it has a noble gas configuration of krypton. Krypton comes after, all right? And that's because it gained that one electron to have the same arrangement of electrons as krypton, but it's not krypton because krypton has 36 protons, but the bromide ion only has 35 protons, and it has 36 electrons. All right, magnesium has 12 protons, neon has 10. They have the same electron arrangement, but they do not have the same number of protons. Okay, so therefore it is not defined by the electron arrangement. The atom or ion is not defined by the electron arrangement, but by the number of protons or the atomic number, as we said in a previous lesson. Okay, let's move on down. And so we should now be good on defining the ground state of an electron, how to write the electron configuration for an atom using the abbreviated full electron configuration, and then just those for the valence electrons. And then you should be able to write the ground state electron configuration for an ion. And make sure you're annotating those. How are these ions formed? Cations, they are formed by losing electrons, and then anions are formed by gaining electrons. And then also make sure you make a note about the noble gas configurations with respect to whether or not it's going to be a cation or anion. So remember, a cation gains the noble gas configuration before, and anion noble gas configuration after. All right, so let's go to our last part, and it asks, how is the excited state electron configuration for an atom expressed? And then we need to define that, and then we just need to have an annotated example so that we can compare those things, and then you should be able to answer the essential question in the summary. So let's go ahead and do that real quick. So here are those same questions. I had defined an excited state electron for you. The excited state electron is an electron that has moved to a higher energy state because it has gained energy from some source. But this is very unstable, and that electron is likely to fall back into its most stable arrangement, releasing energy. But what is that electron configuration, or what could that electron configuration look like while it is in the excited state? And so I have an example here, and these are 3 examples. And so we just want to make sure we pay attention to this. We see that we have a normal electron arrangement. By the way, you should be able to identify this this atom. What would that be if that's a neutrally charged atom? That's right. It would be fluorine, right? It would be fluorine. All right. And then what about this one? Well, you should know this one is a little bit weird. It doesn't follow the electron configuration so neat as this one. 1s2, 2s2. What should this number be? It should be 2p6. And before it gets to 3s2. So what happened? What happened to one of these electrons in the p orbital? Well, it gained energy and it became excited, and it moved into a higher energy level. Is that going to be stable? No. Most likely that electron's going to fall back and release energy. All right, so it gained energy to get to the state. It's going to release energy when falling back. And so we can very easily identify this as an electron configuration for an excited state. All right, and so that's what you're looking for if you were asked the questions about identifying an electron in the excited state. And then here we see an electron configuration 1s2, 2s2, 2p6, 3s1. This looks very normal. It's following a normal electron configuration. We don't see any electrons that have jumped, and so we can see that this would not be expressing an atom that has an electron in it with an excited state, or has an excited state electron. And so this one is 3s1, so this would be sodium. So we should be able to identify that as sodium. All right. Hopefully that helps you answer the essential question, and you are going to get that summary completed, and look forward to having a good day in class. Thank you for watching. Please like and subscribe.